Alright, hell yeah. So we have physics for scientists and engineers, and we have the teeter-totter problem. Now at the end of the video, I'll show the entire problem so you can do it yourself or you can go over it. But what I'm going to go over is the fact that, a viewer was, just looking at this and it's just like, this gives you no information because you're combining too many things at once. What we're going to analyze is this term. We want the angular acceleration, and we know that's going to be the sum of the torques divided by the moment of inertia. And moment of inertia, for me, is hella complex enough because you're just trusting so much in this idea that inertia is some sort of mass, but it's going to be a distance away from a pivot point. And we're going to say, hey, we're going to square that distance. And that's going to give us a representation of that second moment of inertia of mass. This is mass moment of inertia, but it's also the second moment of mass because you take that distance and you square it. That's where that second part comes in. Anyway, and then those are just book values. So if you have this long slender rod, you know that the moment of inertia is just 1/12 ml squared. And you're like, sweet, you know what I mean? And that's what a disc is 1/2 ml squared, And then we just get on with life. And anyway, so when we do that, well, this bottom part, well, and the moment of inertia for this whole thing should just be additive. So we're going to have 1/2 ml squared for the bar, and then plus, well, the point masses. Now, what the hell is moment of inertia? Like, if these are point masses, then we have the mass of the daughter. Let's just do the daughter first. So we have the mass of the daughter, and then we have L divided by 2, and we're going to square that distance. That's like definitionally, that's what moment of inertia. It's second. It's the mass moment of inertia, or it's the second moment of mass. Just a bunch of different ways to say the same thing. But we're going to have the mass of the daughter, and then we're going to take that L divided by 2 squared. And just to get to the problem, all they did in the problem was say, hey, this is downstairs. That's our I term. And then upstairs is the torque. But look at this. Ah, damn it. Alright, so, but downstairs, hey, this is L divided by 2. We got those, but this isn't L divided by 2. So in the problem, what they do is just factor out an L divided by 2. But they almost do like one more step. So we're going to go over that. And now the sum of the torques, like, what's a torque? You know what I mean? Definition of a torque, I like to think of it as a moment. If you do statics, that's just force times distance. And so we're going to have, we have some mass here. And we know that the force due to gravity, Fg, is just that mass times gravity. And then we have that distance. So the moment of the daughter is going to be a torque this way. And then this father is going to be a torque that way. So the torques are going to oppose, and we need the net torque. So obviously, the father is going to create the bigger torque. And so, you could look up here, but we just want to do this intuitively. That's going to be the mass of the father times G times L divided by 2. That's going to be in the positive direction. And then we're going to subtract mass of the daughter, G, L divided by 2. So those are the forces times the distances. And then you can kind of factor this out. So you're going to have, that L over 2 term. And then you're going to have the mass of the father minus the mass of the daughter, and then just times G. Cool, so that's going to be the top part. You're going to have L divided by 2, mass of the father, mass of the daughter, and then times G. And so what we really want to do is just cancel out some L over 2's. And so that's the cool thing about this one is just like, well, how do you do that? So we're going to take this 1/12 m, and we're just going to say, well, what the hell is L? You can always take anything and then just do the same thing to the top and bottom. So that's what I'm going to do. I'm just going to say 2 divided by 2, L squared. And I dig on this because there's one math guy that does just a really good job of, anytime you have a product inside here, I mean, you can do a lot with this. You could say this is 2 squared, L squared, divided by 2 squared. You know what I mean? Or you could say it's 2 well, what do we want? We want to isolate that 2 divided by L. So it's going to be 2, and then L divided by 2. That's what we're interested in. And then we're just going to square the whole thing. So this is going to be, and again, you square the inside. And then, each of those, it's a product that you're squaring. So you square that, then square that. Cool. So now we get 4L divided by 2 squared. But it looks like we got a couple of them, you know what I mean? So what I just want to factor out, oh no, never mind. I don't know what the hell I was thinking. No, these are L divided by 2 squared. I was telling the guy online something different. So yeah, now we're just good to go, and we should be good to go. So we're going to have 1/12 times that mass times 4, and then L divided by 2 squared. You know what I mean? And then if we're combining that with this bottom part, oh, and now we can go a little bit, like 4 divided by 12. Well, this 12, what do we do to the 12? That's going to be 3 times 4. So we're going to have 3 times 4. I mean, I'm just going the extra mile here, but the 4's canceling, you're going to be left with that 3. So there you go. You got 1/3 m, and then L divided by 2 squared. And now you can see that we can cancel out those L divided by 2's. So we're going to throw this value into right there. Just pretend like we did that. And now we're going to cancel out the... So you can only cancel out one of them. That's right. So you can only cancel out one of them. Cool, well, let's do that. So at least we're going to cancel out one. And we're going to have that upstairs. We're still going to be left with L divided by 2. So that we at least need to factor that out. So in each of these terms, we'll still have a L, because all we can do is just cancel out the squared. But we can factor out the L divided by 2, so then we get 1/3 m, and then plus mass of the daughter plus mass of the father. So there you go. That's the m divided by 3 term, mass of the daughter, mass of the father. And then this is an L divided by 2, so they just do like one too many steps at once and then just bring the 2 upstairs. So, holy today, this is kind of a rough video, but that's alright, you know what I mean? We'll get better. And so there you go. So now you get that classic m divided by 3. We'll put the mass of the father first and then the mass of the daughter just like it is. Oh, and then I totally forgot to, you know what I mean, obviously we still have that L term. There you go. That's how they got, you know, they just did too many steps at once. You know what I mean? If I was doing this, yeah, I don't have any more paper, but I just wouldn't do it that way. I wouldn't write it like this. I don't mind big equations. So let's see what we would do if we're okay with just having a big equation. I mean, yeah, you're just gonna have the torque. Again, the torque for the father is going to be bigger, so it's going to be mass of the father times gravity times that distance, and that's going to be L over 2. And then you're going to have minus the mass of the daughter times gravity, L divided by 2. So that's the sum of the torques in general. And what they're saying is like, yeah, you're going to have a cosine component because, you know what I mean, if only when they're horizontal is the length L over 2. But if you start to ramp this up, let's say you're at a 60-degree angle. That's always a good one to know. Because if you're at a 60-degree angle, well, you're just half the distance. You're L divided by 4. So that's why you have this cosine theta part. Because if you throw in cosine of 60, well, you're going to get 0.5. And then your L divided by 2 term basically becomes L divided by 4. You know what I mean? You're only getting 50% of that torque. You know what I mean? So where you had this big torque of the net torque of the father, now once the teeter-totter's kind of upright, you know, in a real high angle, well, that torque isn't very much because that mass of that father isn't very far from this axis. And so cool. But I guess you are going to have that, so we can throw that in, that cosine theta. And now we're going to divide by the moment of inertia. And again, we're just going to have the moment of inertia of a slender rod, 1/12 ml squared, plus the point masses. And now we know that second moment of mass, and that's a good thing to just keep reiterating. But we're going to have the mass of the father times L divided by 2 squared plus the mass of the daughter, L divided by 2 squared. And the moment of inertia term, you have to just add up all the moments of inertia, because what we have is motion, you know what I mean, alpha or omega, or, you know, all of that stuff. That means every molecule of mass is moving, and the molecules of mass on the perimeter are moving faster, and all that is accounted for with this term second moment of mass, you know what I mean? So I'm going to do a lot of problems iterating, you know what I mean? So you actually get a fundamental understanding of where that comes from. That's why I just think the simpler the problems, the better with rotational inertia, until, you know what I mean, you graduate and you're able to just be like, oh, hell yeah. But I don't know. That's the thing with math and physics. If someone just says, hey, that's a disk, and that's the moment of inertia. That's a slender rod, that's the moment of inertia. If you can, you know, even if you have no idea where the hell that comes from, but you know how to apply it, that's cool too. Like that'll get you, I think, a lot farther. You know, just having you know, some trust in the equations and being like, hell yeah, you know what I mean. The literature says I can trust that that this relationship exists. I know what moment of inertias are, and then I know the moment of inertia of the system, and now we can just plug and chug and get that. So anyway. All right, so, and that's cool because that's equal to the angular acceleration. And but they just did way too many steps. So this, if you threw in all the values into this problem, you would, and into this problem, you get the same answer. And that's a good strategy that I use. It's just like, hell yeah, get a long equation that you know is probably very accurate, you know, and then get a value on it, and then start to simplify through, because you might make mistakes. You might be like, oh, what's 4 divided by 12? Is that 1/4? You know what I mean? Like that's a mistake that I would make. But that would pop out, because then when I actually threw in the same numbers into both these equations, I might get 2 different answers, and I'd know I'd have some sort of error. Okay, so that's that. And these are cool, where it's just like, you know what I mean, you have a textbook, and they just do way too many steps at once. So, I mean, this equation is absolutely meaningless. And that's like, you know, it's not meaningless to this problem. You know what I mean? So what this equation says is now we can... Alright, sorry, camera cut out. But yeah, we'll go over, when you get an equation like this, you know what I mean? Hey, it is for this problem, which is cool, because now you can vary the mass of the riders. You can vary the length of the teeter-totter. You can vary the mass of the teeter-totter. You know what I mean? And then you can start at different angles. That's interesting, because even if you start this at a steep angle, you could be stopped. That means your angular velocity is 0. That's cool, but what you're finding is angular acceleration. It's like give yourself 1 second, and you will be moving. You know what I mean? And if you're vertical, you'll be moving kind of slow, because we already went over that. That cosine component really makes the torques if your torques go to 0, you're not going to have rotation. You know what I mean? So at a 90-degree angle, it's going to be maybe unstable balance, but you're not going to have any acceleration. And so, but yeah, that's the cool thing about having equations. You can vary now anything. But then it's also the limitation of equations. You have to be very careful that, hey, this equation only works with this specific problem. So that's what we do for other videos, where we analyze, well, sure, it's cool to get an equation with letters, but it's only useful for that setup. But yeah, and then you can see what you can vary in that setup. Alright, so we gotta make this video shorter. So thanks for joining me, and that's a video. Oh man, I almost forgot to show you the entire problem. So here it is, you know what I mean, you can read it. The problem kind of hinges on this relationship. Well, I don't know. I mean, I guess they get into angular momentum. Yeah, because if you want to find the speed at any point, the angular momentum of the system is the moment of inertia times omega. But this was an interesting thing to read, because, and angular momentum is only equal to I alpha if a rigid body rotates about an arbitrary if it rotates around an arbitrary axis, the angular momentum, which is a cross product between angular momentum is a cross product between distance, from a central point to something that is moving, a mass with some sort of velocity. So it's a cross product between distance and velocity. So that velocity is a vector, and this is going to give you a vector. A cross product does give you a vector, so anyway, that's fascinating. That's why, in our problem, if you have a teeter-totter, everything's rotating about a plane. So if you had a teeter-totter where you went up and then you started to move sideways and then come back, or something like that, I don't think I guess just that's all they're talking about is this equation. This equation, it might not apply. Holy Toledo. But here's the second page. I'm just trying to learn more about rotational inertia. And it's just interesting how you can do simple problems, but still you kind of want to know what happens with the more complex problems. Even from the get-go, you want to know what happens with the more complex problems. So heck yeah. But anyway, I'm just going to leave this up because they ask a couple questions. It's like, hey, if you do have an unbalanced and you are having a net torque, I think they ask, what will balance the teeter-totter? What distance away does the father have to be from the origin? And it's you know what I mean? If they're already at half the length, well, the answer is like, well, it's going to be a ratio between the mass of the daughter and the father. So that's cool. If the daughter weighs half, then the father has to be halfway. And we do that a lot. It's just like, you know what I mean? If we have if you have a bridge, you know what I mean, and I put all the weight right here. Is anything happening over here? Hell no. You know what I mean? But then if I go out a cantilever and then put that same weight, well, sure, won't you have to hold down, if you're trying to hold this in place, won't you have to hold down with the same weight that I'm doing? Yeah, for sure, for sure. And let's say I go out double. We all kind of know cantilevers, you know what I mean? So now I'm going out double the distance with that same weight, you know what I mean? That same W. But no, you're going to have to hold this thing down with 2W, you know what I mean? So the same principle is happening. And then the opposite, you know what I mean? So if this person weighs, a certain amount W, and then I'm just right here at the halfway mark, and if they're going down and I have to hold this thing down, then I have to hold this thing down with 2W, you know what I mean, to prevent this movement, you know what I mean? That's a statics problem. And so yeah, that's kind of fascinating that they solve this statics problem from the torques to be a net torque of 0, but they at least spell out the torques. Like obviously this D has to cancel this torque. I've not really done this problem at all. So I kind of find that interesting. Yeah, because, I mean, if the torques have to cancel, in this torque's mass of the father times gravity, times, and this one's mass of the daughter times gravity times L divided by 2, and now you had to cancel these. Well, yeah, if the masses are different, so, yeah, how would you cancel it? We're basically saying, though, let's do that one, because that's fascinating to me, and I bet you we could do it kind of in a simpler way. So we have the mass of the father times gravity over here times some sort of distance is equal to the mass of the daughter times gravity, L divided by 2. And so we want to know what this D term is. Well, we could just solve for it. You know what I mean? The gravity cancels, and then D is just mass of the daughter divided by mass of the father, L divided by 2. And so that's what they get down here. I'm just surprised they would actually go to all that trouble. I don't know what they're at. I don't read textbooks very much. But if you just have a net torque, we obviously know that a net torque of 0 causes no motion. You know what I mean? That's a statics problem. And so that distance would turn this into a net torque of 0. Yep. Yeah, so, I mean, what they did is like, oh, cool, we have this entire thing. Instead of saying net torque is 0 and getting there, you know what I mean? Like, you're just setting this equal to 0 and calling it a day. They say, well, the acceleration, the angular acceleration, we're not going to have any angular velocity in radians per second is going to be 0, and we're not going to have any change in radians per second. You know what I mean? So our acceleration, this equation is going to be 0. And if you do that, I guess, yeah, you have to go through all the different terms and then get them together. But everything is going to cancel, and you're just going to have that. Cool. Alright, so that was a pretty satisfying end to that video, not to make it too much longer. Thanks for joining me, and that's a video.